Thank you all for joining us today. My name is Michaela McShane, and it is my privilege to welcome you to the Startup NASA Feature Series, hosted by NASA's Technology Transfer Expansion Program. T2X expands the tech transfer mission of ensuring that innovations developed for exploration and discovery are broadly available to the public, to include a focus on entrepreneurial innovation and strategic partnerships that accelerate commercialization. This monthly series is an opportunity for NASA technology-inspired startups to share their experience. This month, we'll hear from Elementum 3D. First, I'd like to point out that the audience microphones will be muted throughout this presentation, so please type your questions in the chat box in the lower right-hand corner of your screen, and we'll answer them at the end. Thanks for joining us, and I'll go ahead and introduce today's speaker. It's my pleasure to introduce our speaker, Dr. Jeremy Iten, the Chief Technology Officer of Elementum 3D, where he leads the company's materials and technology development. At Elementum 3D, he co-invented reactive additive manufacturing and guided development and commercialization of a dozen new alloys for additive manufacturing. With more than 2 decades of leadership in materials science, his work spans reaction synthesis, powder metallurgy, welding, and additive manufacturing for applications in space, aerospace, defense, automotive, and energy. Jeremy earned both his PhD in materials science and his MNG in metallurgical and materials engineering from the Colorado School of Mines, where his research focused on reaction synthesis of advanced materials and novel exothermic welding technology. Throughout his career, he has led multidisciplinary engineering teams to bring new products from concept to market, including securing competitive R&D funding and transitioning and qualifying technology in customer applications. I'm going to turn it over to Jeremy to tell us about Elementum 3D.
Yeah, thank you. Let me share my screen. All right. So first, I want to start with thanking the NASA Technology Transfer Program team. It's been a pleasure to work with Hia and Michaela on this webinar, and also Margot on the spin-off article. And I want to direct everyone's attention to that spin-off article. You can access it at the URL shown at the top of the screen. And if you don't have a chance to capture that full URL, you can also find it right on the front page linked on the spinoff.nasa.gov website. So we really appreciate the effort and the team at the NASA Technology Transfer Program that went into putting all this together. Elementum 3D's core business is the high-performance AM metal feedstock powder supply and development. Along with that, we also do AM process and application development and qualification. We work directly with customers to help them make their products out of our materials. We have print capability in-house as well. And one thing that we're proud of is we actually were the gold medal winner in the U.S. Air Force's Rapid Sustainment Office's Advanced Manufacturing Olympics with one of our materials, our A7050 RAM2 alloy. Elementum 3D is located in Erie, Colorado, just north of Denver, east of Boulder. We have 2 facilities, about 10,000 square feet each. We were founded in 2014. We have over 27 technology patents, 40 employees, over 220 customers, and a 400-ton annual powder production capacity. As mentioned, we have metals additive manufacturing print capability in-house in addition to our powder capability. We have an advanced aluminum atomization system that is coming up to be completed here soon. And we also have a metallurgical lab with further capabilities. We're AS9100 quality certified, ISO 9001 2015 as well. And then DFARS, NIST 800 171 cybersecurity compliant, ITAR registered, and so on. So our materials are helping power the next frontier. We have our materials being used for critical applications in areas including space, Formula One racing, energy and aerospace, defense, and other areas too, including taking the silver medal with the downhill World Cup mountain bike that utilized printed components out of our material. So Elementum 3D has a deep history with NASA. Our relationship started with the Jet Propulsion Laboratory, who reached out to us as our very first customer. They wanted to test some of our printed aluminum metal matrix composite material So we printed samples that were then tested for performance over at JPL, working with Doug Hoffman there. And that was great to have our first customer be NASA reaching out to us. We also participated in other projects like building additively manufactured excavator blades to test different material performance for exploration of icy planetary bodies. This relationship evolved to JPL's qualification of our A6061 RAM2 material for space missions. This material was recently used by JPL to produce parts that were launched on the Europa Clipper mission. These parts were the very first ever to fully meet the NASA 6030 production standard. So that's another thing we're very proud of. We've also done work with the Glenn Research Center on development of printed soft magnetic materials for Hall effect thrusters and other space and terrestrial applications. And we've been working with Dr. Tim Smith, Christopher Cantles, and the team at Glenn who invented the really great new oxide dispersion strengthened superalloy called GRX-A10. So a little bit of the history there. I was on vacation when I saw a news article about this alloy, and I immediately reached out to the lead inventor, Tim Smith, to learn more. He put me in contact with Amy Hiltebeitel at the Glenn Research Technology Transfer Office, and she stepped me through the process to initially get a research license for the material. We then performed some of our own testing and development with the material, which led to us applying and being selected for a co-exclusive commercial license to produce and sell the material. So we're now commercially producing this material and delivering to customers. And it's really exceptional material with a nano yttria coating on the base superalloy feedstock. And it has very exceptional high temperature performance. So Amy and the Technology Transfer Office was fantastic to work with through the licensing process. And Dr. Tim Smith and the technical team at Glenn continue to be very helpful in sharing their knowledge and collaborative assistance towards additional characterization and data collection with the commercial material. We also worked with NASA Langley Research Center for E-beam freeform fabrication, along with Professor Stephen Liu and his graduate student at the time, Iten Sullivan, at the Colorado School of Mines on development of wireform RAM aluminum products. So following this work, we spun out a company ourselves called Fortius Metals, who now produces and sells RAM alloy wire feedstocks for wire DED process and also for high strength welding applications. And we have a really great history with NASA Marshall Space Flight Center that started with Elementum 3D working with Masten Space Systems, now part of Astrobotic, on a NASA tipping point program where we developed and tested a regeneratively cooled aluminum metal matrix composite rocket engine with extremely high thrust to weight ratio that's suitable for travel to Mars. We again worked with Marshall Space Flight Center and Masten on an SBIR Phase 2 program for development of PermeAM technology for improved fuel injection and transpiration cooling, which offers also a controlled pressure drop and simplified design integration for rocket engines. The technology is highly enabling for liquid rocket engines, but it's also useful for other combustion engines, thermal management, filtration, catalyzation, and other commercial applications. We worked with MSFC again on development and testing of large format powder bed fusion additive manufacturing of GRCOP42 rocket engines. GRCOP42 was initially developed by Dave Ellis at NASA Glenn Research, and then later championed for additive manufacturing by Dr. Paul Gradle, principal engineer at Marshall Space Flight Center. We also worked with propulsion engineer Thomas Teasley on this and others, really printing innovative engines from this material. And this development translated into wide use within the commercial space industry. I also want to mention the excellent additive manufacturing textbook, Metal Additive Manufacturing for Propulsion Applications, that was put out by Paul Gradle and the team at NASA. You can purchase this book today online, and I was fortunate enough to have been invited as a co-author for one of the chapters in this book. And this book is really great for additive manufacturing in general, even beyond propulsion applications. We further collaborated with MSFC on development of A6061 RAM2 aluminum alloy for blown powder DED AM for large-scale components for propulsion and other applications. This NASA team was led by Paul Gradle and included Tessa Fedotowsky, Ben Williams, and Darren Tinker, and we'll talk more about this ACO work in the upcoming slides. So first, what is this RAM technology that I've been mentioning? So RAM is reactive additive manufacturing, and it's patented technology at Elementum 3D that's inspired by reaction synthesis. So we're using reactant phases to form product phases in situ through energetically favorable reactions. This enables use of traditional micron size AM reactant powders while forming submicron or nanoscale products in the printed parts. This helps to achieve full density in the printed products, and also helps to improve the strength, the elevated temperature performance, wear resistance, and reduce the coefficient of thermal expansion for the printed materials. Allows for tailorable properties. We can change the properties of the material based on the amount of reactive additions we put in. But one of the most important things is that for many alloys, it makes unprintable metals printable. And I'll get into this on the next slide. So many alloys, including most high-strength wrought aluminum alloys, are not autogeneously weldable, and therefore they're not printable with a laser powder bed fusion or a fusion type process where you're essentially doing a layer by layer welding process. So if you wanted to weld one of these high-strength aluminum alloys, you would probably need to use a filler metal of a different composition, or maybe you wouldn't want to weld it at all, and you would instead try and rivet it or otherwise fasten it together. So this is, of course, a problem when you're doing layer by layer welding in additive manufacturing. So because of this, most of these traditional, very desirable high-strength wrought alloys for aluminums and many other materials are unprintable or unusable today without changing something. So we've been able to use reactive additive manufacturing to make these alloys printable with properties that meet or oftentimes even exceed their wrought legacy counterparts. In the colored images there, those are EBSD images showing the grain structure of the printed materials. And you can see on the left, that's the legacy 6061 aluminum composition alloy. When printed, you get this columnar grain structure with a high degree of texturing and orientation of those crystals. And you get cracking in between those crystals, making it unusable, functionally unusable. Once you add in RAM to like a RAM1 or RAM2 type level, that 2 in this case represents a nominal volume percentage of the product phases formed in the reactive process. You get a very fine equiax microstructure. Now you've eliminated that columnar texture, you've eliminated any cracking issues. You get a cross-sectional grain diameter, in this case, under 2 microns. So very fine microstructure with great properties. If you go to a RAM10, that's again a nominal 10 volume percent of the ceramic product phase. You don't get a lot of further refinement because it's pretty much fully refined by 2 volume percent, but you do continue to get increased strength, increased stiffness, wear resistance, and elevated temperature performance. So there may be reasons to go even higher, but with the RAM2, you're typically getting comparable or slightly improved properties compared to the wrought counterpart alloys. The same process is also useful for other alloy systems, including nickel alloys. A Haynes 230 type alloy system is one that's also known to suffer from solidification cracking when printed by a laser powder bed fusion type process. Again, you get these hair-like cracks that you can see in that microstructure, and again, due to the columnar solidification texture that you get. With our RAM process, we've been able to eliminate that cracking, greatly improve the performance, and get much more reliable and improved properties from this. This work also involved integrated computational materials engineering together with the Colorado School of Mines and was supported by the Office of Naval Research. Now, getting back to our NASA RAMFIRE ACO. ACO stands for Announcement of Collaboration Opportunity, and RAMFIRE stands for Reactive Additive Manufacturing for the Fourth Industrial Revolution Exploration Systems. Development of A6061 RAM2 blown powder laser DED production capability was the real goal of this project. And for the project, we produced 2 regeneratively cooled nozzles that were then subsequently hot fired. Also an aerospike concept nozzle that you can see me holding in the bottom right corner. And channeled cylindrical vessels with isogrid style reinforcement. The nozzles included welds to ROT 6061 manifolds, including an A6061 RAM2 wire TIG weld. So the 40th metal spin-out wire was used to weld some of these materials. I'll touch on that a little more later as well. And the nozzles were tested in multiple hot fires with hydrogen and methane fuels. And you can see the assembly there below. The part on the right is the DED printed nozzle from the aluminum RAM material. In the center is a GR-COP 42 combustion chamber. We also produced that. And then on the left is a GRX 810 injector component. So this was really a merger of 3 advanced AM type technologies, and I think a really great, exciting project to be a part of. So these are the cylindrical vessels that were printed using the isogrid style reinforcements. You can see on the left is an image of the printing process in progress. The printing was done with partner RPM Innovations. And so this is using a blown powder directed energy deposition process. So you're basically spraying the powder at the part and then hitting it with a laser to fuse it into the part with using a robot to control the tool pathing. In the center, you can see a diamond type isogrid around the outside of that part. Again, to give the scale, it's about 36 inches in length, so it is quite sizable. It's bigger than you'd be able to print in a typical laser powder bed fusion type bed system. But with the robot DED assembly, you can get very large, 20-inch diameter. And then on the right, that part there is shorter in height, but the same diameter, and you can see that's a hexagonal type grid structure. So again, on the left, you can see now the RPM Innovations blown powder DED system producing, in this case, the aerospike concept nozzle. It's a very large concept part, thin-walled with regenerative cooling channels throughout. And then on this image on the right, you can see the shiny interior surface that was finished with REM surface engineering using their REMChem type process to surface finish that part to a polished, almost a mirror type surface finish. This is a 36-inch diameter part, so again, quite large. Here's the steps for the manufacturing of the A6061 RAM2 RAMFIRE nozzles. So on the upper left, you can see the laser powder DED nozzle being produced. After the production, you can see the nozzle there in the second image. The part was laser scanned to confirm that the geometry was correct according to the CAD model. And then there was TIG welding to weld a ROT produced manifold structure to that chamber. The manifold could have been printed directly on there, but it's basically a big bulky piece of metal, and it was more cost effective to produce that through other processes. And then this was an opportunity to demonstrate the ability to join a traditional legacy ROT 6061 component to the printed RAM2 component and use the high strength 6061 RAM2 wire to do that to get a weld strength that otherwise would have been unachievable. There's the part in the bottom left after the heat treatment process. And then there was some machining of the manifold and the nozzle at the joint in the weld. So there was then subsequent flow and proof testing of the component, followed by the hardware installation, and then the hot firing, which I'll get into later. Here's some more on the RAMFIRE welding that was performed. And so on the left there, you can see this was a 6061 wrought plate, traditionally produced plate, with that was welded with 6061 wire without any RAM in it. And you can see that there's a big crack along that weld bead, and in the cross section there, you can see the cracking that took place. So this is the problem that we're trying to overcome for the welding side, and printing has similar challenges. So what we did is we used now our RAM reactive constituents in a wire that was produced by our partner, Fortius Metals. And you can see a spool of that wire in the bottom left. And now we were able to take 6061 wrought plate, weld it with this 6061 RAM2 wire, and avoided that cracking problem. So this concept was then used for welding the manifold to the printed DED nozzle. So a TIG or gas tungsten arc welding was used to weld the flange with the wire, and you can see the weld that formed was very, very nice looking, very high quality, and it held up well in the hot firing as well. You can see the image on the right. There's frost all over it. That's because of the cryogenic fuel and oxygen that was being flown through the parts during the hot firing. So here's some images from the hot firing that took place, and you can see a short video of some of the hot firing from the spin-out article I mentioned earlier. So in the upper left is the methane fuel. In the bottom left is the hydrogen fuel. And on the upper right is a thermal imaging of that methane fuel hot fire. And then you can see the nozzle and chamber in the bottom right image, all covered in frost from, again, showing the effectiveness of the cooling of the regeneratively cooled nozzle. Basically, you're flowing the cryogenic fuel and oxygen through the part to keep the part cool. You get some preheat to the fuel as well before you combust it. And that's how you can make a rocket engine nozzle out of aluminum without melting it. And it also is really why additive manufacturing is so beneficial for these regeneratively cooled rocket engines, because it's very difficult to make through traditional processing because you're using conformal cooling channels throughout the part. And I just want to touch also on some of Elementum 3D's materials capabilities. So I talked a lot about our aluminum alloys today. We offer products in 1000 series, 2000 series, 5000 series, 6000 series, 7000, and 8000 series aluminums. These products in general, these types of alloy systems in general would be unprintable without the RAM technology. So we're enabling these types of materials to be printed today. These are all most of these are common alloys that are used for legacy parts, but otherwise you couldn't make added parts with comparable alloys to these. We also offer aluminum metal matrix composites, where we're really increasing the ceramic amounts to take advantage of that high strength, high modulus, high stiffness, and really good elevated temperature properties from that ceramic metallic composite structure. We offer a family of nickel alloys as well, including nickel 230 RAM, Inconel 625 RAM, where as I mentioned, a co-exclusive license holder for production and sale of the GRX 810 material. And we work with other specialty nickel alloys like Invar 36 as well, which is a very thermally stable, dimensionally stable alloy. We work with copper alloys. We've developed the very first printable, commercially pure copper product on the market. Copper is a difficult material to print, both because of the high thermal conductivity and also because of the very poor laser absorption of the material. And so we've been able to functionalize pure copper for printability. We offer copper, aluminum, bronze, cupro, nickel, and have done a lot of work in the area of GR COP 42 as well with NASA and also with private space. And we have a high operating temperature copper product using our RAM technology that we'll be releasing in the near future as well. We've done a lot of work with refractory metals, including tungsten, tantalum, rhenium, and molybdenum. and also done work with steels. We have RAM improved steels, and we've also done development on other high performance steels. So I want to say thanks again to the NASA Technology Transfer Team for hosting this webinar, and to NASA and our collaborators on helping make this technology possible, both for space exploration and also for the commercial market. I think we should now have time for questions.
Thanks, Jeremy. Yes, we've received a couple of questions from the audience, so I'll go ahead and get into those. And do feel free to continue submitting questions while we go, and we'll get to as many as we have time for. Okay, so first question. For startups considering licensing government developed technology, what advice do you have on navigating the licensing process and forming productive agency relationships?
Yeah, great question. So I think the first step is, make sure that the technology you want to license aligns with the goals of the company. Do you have expertise in that area that can help support the transfer of that technology and commercialization of it? If not, I think that's something that you should certainly consider having on board on your team as well. As far as the process, for us, we just directly reached out to the inventors, to the technology transfer offices, and expressed our need. Some of the things that they're going to want to know, of course, are, what does your company look like? Are you a one person company? Do you have the infrastructure? Do you have a sales team? Do you have the ability to produce products from the technology? Do you have the expertise to be successful at that? And so what is your commercialization plan, pathway? All those things are going to matter. Hopefully those are incorporated into a business plan. But especially with NASA, we found that it was, really they helped step us through what was needed from them. It was very clear. We had a lot of this capability in place already from our commercial materials that we were already offering. But I think it was very friendly to work with them, and you just need to make sure that you have the infrastructure and preparations that you can be successful with the license. And I think if you can show that, then it should go smoothly.
Awesome, thank you. Let's see. How did you go about fundraising in the early stages of your company?
Yeah, so initially it was friends and family. And then beyond that, we had demonstrated our technology. Initially, we couldn't afford an $800,000 metals 3D printer. So we got a laser engraver system. We modified it into a makeshift 3D printer, put it into an argon-filled glove box, and we started printing coupons and representative samples of different reactive additive manufacturing material systems. And then we tested those materials, did X-ray diffraction, did other microstructural investigation and testing of it. And then we reached out to one of the printer manufacturers and wanted to talk with them about what we had to see how we could go about getting a real metals 3D printer in-house. That printer company decided that what we were doing was quite unique and looked very innovative and like a good opportunity. So they agreed to put our first printer in our facility on a convertible note type structure, so that we didn't have to pay for it up front, and then later that equity it could be converted into equity in the company for that printer. So that was how we initially started, and then
there we go.
Did I cut out there for a second?
Just for a sec, but it sounds like it's okay now.
Okay, yeah. So that's how we started, and so we got our first $800,000 metals 3D printer from the printer manufacturer company, from their owner and their group that believed in what we were doing. And then from there, we were able to get a hold of and meet with other investors and did subsequent investment rounds as well.
Awesome, thank you. Let's see what we have next. Would you have any post-operations microstructure of the additively manufactured material? I'm not sure I understand that question. Does that make sense to you?
Yeah, certainly we have lots of microstructure available. And it does depend, of course, on the material we're looking at. So you saw the EBSD images, so that's kind of representing the grain size. And what you'll get is you'll get, well, let me go back. I think, yeah, so if you can see this slide, you can see that bottom center image. That is a 6061 RAM2 laser powder bed fusion printed material. The 6061 RAM2 DED produced material is very similar to that. The grain size is slightly larger, but in general, it's very similar. You can see the white phases. Those are the some of the ceramic formed phases. In this case, titanium diboride, which is a very high temperature, very hard ceramic type phase, and those are on the order of maybe 100 nanometers in size. And those are serving as nucleation sites for the aluminum to solidify around and grow out of. So you have a very fine microstructure overall. Let me show you on this slide as well. There's a top right microstructure. The left is a non-RAM microstructure with the cracking. The very top right, that is a 10% volume fraction ceramic phase microstructure. And you can't see the scale on that. I apologize, it's quite small. But it almost looks like a little bit like concrete, only on a much smaller scale, on a micron scale instead of a macro millimeter type scale.
Awesome, thank you. The next question asks, do the RAM inclusions only benefit in processes requiring melting, or would they still benefit in solid state processes?
Yeah, great question. So I think the dispersion strengthening that they offer would also benefit in solid state type processing. You don't have the same solidification cracking issues to solve in those types of processes, but you're still creating a metal ceramic dispersion strengthened material. So I think when you then take those products and you heat them up to high temperature, you apply stress, the ceramic dispersion strengthening will pin dislocations and will increase the strength for those types of processing as well.
Thank you. Let's see. There's a question about battery technologies. I'm not totally understanding the way that it's phrased, but it seems like they're looking for your perspective on battery technologies and related industries.
Yeah, so we're not directly involved at Elementum 3D with any products in the battery technology area, but we are selling materials to companies who are working in those areas. I think the materials themselves, depending on what you're looking for, they can be good structural constituents for batteries. They can also be, good other functional materials for battery components. And I think the permeam technology I mentioned also could be an interesting one to look at in battery technology.
Thank you. And for everyone asking, this will be recorded and you will receive a link to the recording once we wrap up later today. So if you have to drop off early, you'll be able to get the rest. Okay.
One other thing just to add to the battery technology area, I think thermal management is one great area that these could be really useful. You can build cooling structures conforming to the battery assembly that can be extremely helpful with this type of technology.
Thank you. The next question asks, what is the repeatability of the RAM process? RAM process.
Yeah, it's highly repeatable. We've done some qualification efforts using multiple printers with multiple feedstock lots, multiple heat treatments, and so on, and we can collect very consistent data across all of these different builds. I think that's the big thing about the RAM process is because you're generating this very fine equiax microstructure, you get very consistent properties. With a columnar type structure, one of the issues is you'll have different properties in the Z or growth direction versus in the XY or in plane direction. Whereas with the RAM process, because the microstructure is so consistent, the properties are also very consistent across different directions.
Thank you. Okay, next question. Do you find a significant decrease in ductility as you increase the RAM percentage?
Yeah, so as you go up to higher ceramic volumes, that is the trade-off between like a RAM 2 and a RAM 10. Depending on the starting material, you might still have very good ductility at RAM 10. But if you're starting with a less ductile material, as you do increase the ceramic percentages, you do tend to lose some of that ductility because you're really kind of getting a combination of the ceramic and metal properties. Ceramic, of course, is not ductile on its own. And so you're taking advantage of that metal matrix around the ceramic for the ductility. But as you add more and more of the ceramic phase, you do tend to get a reduction in ductility as you increase your strength from the additional ceramic.
Thank you. Can you expand a little bit more on the fatigue properties and long-term elevated temperature exposure?
Yeah, fatigue properties are actually very good, generally in line with wrought materials. And I do have a supplemental slide I can show on that even. So here's some of the fatigue properties. Well, I'll start with this one. This is a case study around combustion engine pistons. In this case, it's a motorcycle piston, but it can also be used for race cars or any automobile type applications. In this case, you can see the fatigue chart on the bottom right. The blue squares is in this case, it's a 2024 RAM aluminum. Whereas the red circles are a traditional cast aluminum alloy that's used for pistons. And basically what you're looking at here is the stress and the cycles to failure. And so at a much higher stress, you get much increased cycles to failure compared to the traditional cast aluminum alloy in this case. One other thing to mention is this fatigue chart here is at 250 degrees Celsius, which is an operating temperature for these combustion engine pistons. And one unique behavior is that you start to see a certain stress threshold with some of the higher RAM fractions, where the material starts to behave more like a BCC type material or like a steel, where you get a fatigue limit, where below that stress your cycles start to go and approach almost infinity, where it's really hard to fatigue the material below a certain stress threshold. That's not normally the case for aluminum materials. But with the higher RAM amounts, these composite type materials tend to exhibit that fatigue limit type behavior. Here's some other fatigue data for an A1000 RAM 10. It's compared against an ALSI 10 MG printed material for comparison. And then a 6061 RAM 2, which is the material we've been talking a lot about with the ACO blown powder DED work. And you can see that the green is the RAM 2, and it's being compared against the MMPDS data for the aerospace data for the traditional wrought 6061 in the T6 heat treatment condition. And especially at the higher cycles, you can see that the RAM 2 material compares quite favorably. These points on the very right are all run out points where basically the test was stopped without the parts failing. And on the very right, you see 7050 RAM 2 material also compared against the MMPDS aerospace data set. And again, the printed RAM 2 material compares quite well in fatigue.
Thank you. Okay, you mentioned certification to NASA 6030. Is compliance to this specification applicable to an AM process material, or is it also part geometry specific?
Yeah, it goes into the actual part production. So there are aspects going all the way down into the feedstock that's being used, the process. So it's controlling the feedstock, controlling the process, and then also controlling the part and qualifying the part. So it's a really great, pretty comprehensive spec. And you know, I think it's one of the best specifications for additive manufacturing today.
Thank you. Okay, next question. For refractory metals, is there any printing being done with these metals, or what work do you do with refractory metals?
Yes, we are involved in refractory metals. We try and operate in the space of novel materials that are not the standard ones, the Ti-64 or the base Inconel 625 that are commonly used. But we've done quite a bit of work in refractory metals, tungsten, tantalum, rhenium, and molybdenum. We did recently complete a DARPA program developing some of the very first 3D printed rhenium material, and that's a fun one to work with.
Thank you. What about the corrosive behavior of such small grain-sized RAM processed AI 6061?
Yeah, in general, the corrosion behavior is similar to the base alloy, the wrought legacy counterpart, but there are some differences because of that fine grain size. In a lot of ways, you tend to get more uniform corrosion because of the very consistent fine grain size. But you can sometimes get a little bit increased corrosion rate because of the increased grain boundary area as well. There's some publications out there. I don't have that information right in front of me today, but there are publications out there that are looking at the corrosion behavior of some of these printed RAM materials. And in general, it's quite good, fairly similar to the wrought counterparts, but there are some differences.
Thank you. Since RAM reduces feature size in microstructures, does RAM potentially enable reliable printing at higher resolution?
Great question. So we have found that we get very excellent surface finish with the RAM materials because you're not having that texture that can form with the larger, and columnar type grain structures with many materials. So surface finish wise, definitely it can be helpful. As far as feature size wise, that's something that I think oftentimes is a limitation of the printer itself and the optics of the printer. But I think it might make sense that that it may be very suitable to that very, very fine resolution because of the fine solidification grain size. So I think that makes sense. I don't think we have a lot of testing in that area below what some of the standard printers today can do as far as feature size.
Thank you. Okay. The next question asks, for those interested in qualifying parts with these RAM materials, does Elementum offer printing services for prototyping and qualification? If not, is there someone you work with who offers these services?
Yes, we definitely help with that. We have in-house printers. We help customers directly with first articles, help them with initial prototyping, qualification, design for AM. We help them get started. We're not trying to be a contract manufacturer ourselves for serial production of parts, and we do have partners that can take on that contract manufacturing serial production aspect. We'd be happy to recommend some of those partners that are already printing our material that can help in that area. And some of those partners would also be happy to take on prototyping and development work as well. We're happy either way, but we do know that a lot of contract manufacturers prefer serial production, higher volume parts production, and that's where we try and help the customer make sure they're successful with some of those first articles and making sure everything is working well before going to the serial production.
Thanks. Okay, I think we are just about out of time for questions, and I think we've got to everyone's. If we didn't, feel free to respond to the email that we send out with the recording if you have additional follow-up questions, or reach out directly to Elementum 3D. We'll close with a question that we like to ask all of our guest speakers, which is if you could offer one piece of advice to someone who's just getting started on their startup journey, what would that be?
Only one, huh?
Just one.
So make sure you know what you're trying to do, and give it your all. I think, don't let barriers, don't let obstacles, don't let challenges stop you. Find ways around there, get good people around you, and make it successful.
All right, thank you so much. We appreciate everyone who came out today and asked lots of very technical and thorough questions. And thank you so much, Jeremy, for taking the time to speak with us today.
Yeah, thank you everyone for attending.
All right, have a good rest of your day.